Hey everyone, I'm going to do a pretty quick video on the golden ratio and continued fractions. I think these are just two kind of interesting topics and they come together just really nicely. And continued fractions aren't usually something that we see just in school or anything like that. And same thing with golden ratio. Most people know the golden ratio as, I don't know, this spiral thing, um, which, okay, sure. That's not really what the golden ratio is, but I mean, it kind of has to do with it. It's all about ratios. So it's a ratio. And what a ratio is, if something is twice as big as something else, I mean, that's the ratio, too. A ratio is just like a number. Um, it's a number that tells you the size relationship between these two things. So I'll mainly focus on just this one dimension. You can see that there's like a two-dimensional. This is a golden rectangle up here. Uh, I'm mostly just going to be talking about this, like line segments. So the golden ratio, like it's a ratio. If an object's twice as big as another object, that's a ratio. If you're three times as big, if you're half as big, if you're one and a half as big, those are all ratios. So what the golden ratio is a specific ratio. And this picture over here actually kind of gives you the idea if you have some explanation. So let's just look at this picture and I'll try to explain the concept of the golden ratio. So the golden ratio is talking about, so here you're going to read right here, A plus B is to A as A is to B. And what that is saying is the total length, A plus B, is to, meaning is in ratio with the A, as is the ratio of A to B. And that's just like a lot of, it feels like alphabet soup when you deal with things like this. So here's the way that I like to think of it. I'll try to say this in a couple different ways so that maybe one of them clicks. So think of it like this. Think of both of them, and then think of A as the big one, and then think of B as the little one. So the way that I think of the golden ratio is both of them together to the big one, that ratio, is the same ratio as the big one is to the little one. And even that's a little bit weird. Like when they start out with this, to me, this is honestly the best way that it clicks in my brain. Uh, and this is the same thing. It's just kind of flipped upside down. The small one is to the big one, as the big one is to both of them. That's honestly the way that clicks the most in my brain, but there was a bunch of different ways that you can think about it. So I'll give you kind of the answer to the golden ratio. So like I said, it's a ratio. So the answer to that question is a number and it's a ratio. It's like twice as big or half as big. There's a specific amount of biggerness that you need to be in order to satisfy this property. A needs to be the golden ratio amount bigger than B in order for the sum of the two to share that same ratio. And it's about 1.6. And you can even see here, take B, and you can put your fingers up on the screen. The length A, it's like 1.5 B's and a little bit more. And then what you'll notice is both of them together, A plus B, it should be, and I don't know, you can use, I don't know how perfect this picture is, but look at A and then add half of A and then add a little bit more. So that's kind of the idea with this golden ratio. And it turns out the answer to this is about 1.6 is how much bigger you need to be. Okay, so that's the idea of the golden ratio. Like I said, it's about 1.62, I guess, 1.618. It goes on forever and ever. So in that way, it's kind of like pi. It's not a transcendental number like pi because it's quadratic. Pi, you can't even write pi with radicals. That's called transcendental. That's what makes pi a little different than phi. So this Greek letter here, phi, some people say phi, but we use phi to represent the golden ratio. And it has this quadratic form, 1 plus root 5 over 2. That's the answer to the question. in order for these ratios to be the same, the big side needs to be 1.618 whatever times bigger than the small side. So you can find this if you just take this equation up here and you cross multiply, you'll get a quadratic. Oh, actually, not this equation right here. You can go read Wikipedia. They walk through how you get the quadratic and you get all this stuff. We're going to talk about something different. First, what I want you to do, just to see if you have kind of a grasp on the golden ratio, quickly look at these lines and tell me which pairs of lines are closest to satisfying the golden ratio. I feel like there's probably two pairs of lines here that are more or less close to the golden ratio, and I feel like there's others that you should be able to say, no, this does not follow it. So I'll give you a couple seconds to think it over. So remember, it's like 1.6. You can think of it that way, or you can think of it as the big side is to the sum as the small side is to the big side, or the sum is to the big as the big is to the small. So, in my opinion, I think it's this one and this one that are closest to satisfying the golden ratio. I'll explain kind of briefly why these ones don't really, and then maybe why these ones do. So let's start on this one right here. So, like I said earlier, the one that works for my brain the most, just in an intuitive way, the small side is to the big side as the big side is to the sum. So here, notice the small side, we would need like 7 of these or something in order to make the small into the big. But we definitely don't need like 7 of these in order to make the sum. Or you could think of it, the ratio of the sum to the big side, it's like barely 1.1 or something, 1.2. And the ratio from the big side to the small side is like 7 or something. So this one over here, maybe that's closer, but I'll talk about this one right here. If two lengths are like basically the same, they definitely don't satisfy the golden ratio, because the big side to the sum is going to be like a 1-to-2 ratio, and then the big side to the small side is going to be pretty much a 1-to-1 ratio. This one, I think just this side is maybe a little bit too big. Remember, the golden ratio, it's like 1.62 if we round, or so one. Well, this looks like 2. This looks like this is more than twice as big as this one. Okay, so I don't know, maybe you can let me know if one of these in particular looks like the best to you. So what we're going to do for the rest of this video is show you how we can think of phi, the golden ratio, as a continued fraction. So first let's derive what phi is. First, let's let A be the big side, and let's let B be the little side. So what the golden ratio tells us is the big side, A, I should make that look nicer, the big side divided by the little side is the same ratio as when you put them both together. Algebraically, we say A plus B, right? That's the small and the big together, is to the big side. And this is phi. Phi is equal to A over B, which is equal to A plus B over A. So what we're going to do here is called a substitution. And what a substitution is when you write certain symbols using other symbols. But you have to follow math rules. You can't just like make up the rules as you go. So what I mean by that is phi right here is literally equal to A over B. So instead of writing A over B here, I can literally just write phi, and we haven't changed anything. And you'll see we do stuff over here. We're going to write A plus B over A in terms of phi. So then you'll see we actually have to do stuff. So first what we should do is, well, we can break up that fraction. When you have a sum over a fraction, what you can do is you can break up that sum over the fraction just like this. I'm about to do right here. Just like you can bring together two fractions that have the same denominator, if you have something like this over one denominator, you can break it up. So let's do this. And now what we can do is simplify. A over A is just 1. And what we're going to do is we're going to write B over A, and this is where we do a substitution. we're going to write b over a in terms of phi. Phi is a over b, but we want to write b over a in terms of phi, but we see that it's just upside down, right? If you want to write b over a, but you have a over b, you got to flip it. You got to make 1 over. So that's why 1 over phi is equal to 1 over a over b. But if you do 1 divided by a fraction, it's the same as multiplying by the reciprocal. Reciprocal means flip the fraction. That's why we do have this. 1 over phi is the same thing as b over a. So here we have this interesting, this is a self-referential, is that the word? We have an equation for phi in terms of phi. And this is going to help us, this right here is going to help us get a recurring fraction for phi. So here, let me save that really quickly, erase the whiteboard, and start again. So phi equals 1 plus 1 over phi. And what we're going to do here to get the continued fraction is we're going to do a series of substitutions. And so this seems kind of weird, but here's how the substitutions work. Phi is equal to 1, this whole stuff over here, 1 plus 1 over phi. Phi is equal to 1 plus 1 over phi. So what we're going to do, let me copy and paste this so I can show you what the idea is. Phi is equal to this. So when we see this phi down here, what I'm going to do is I'm going to replace it with this, because this is what phi is equal. This equation right here, phi is equal to 1 plus 1 over phi. So what I'm going to do, when I see this phi down here, I'm going to replace it with 1 plus 1 over phi. So that's what we do. So instead of phi right here, I'm writing 1 plus 1 over phi. Right? Because phi is equal to 1 plus 1 over phi. So instead of phi here, I have this down here. See? So this is kind of like scratch work over here. You can kind of ignore it. So what we do is we continue this process. And what you'll see emerge is that phi actually has probably the most natural of all continued fractions. So this is probably the first time that a lot of you have even seen a continued fraction before. But this interesting thing that comes out of the golden ratio is that it has the most natural continued fraction that you could think of. Nothing but ones. So let's see how we get that. This next step, see, instead of a phi here, I'm going to write 1 plus 1 over, phi is equal to 1 plus 1 over phi. So instead of phi here, I'm going to write 1 plus 1 over, but then instead of phi, I'm going to write 1 plus 1 over phi. But then instead of phi, I'm going to write 1 plus 1 over, but then instead of, and you see how this keeps going forever? Every time you replace a phi with 1 plus 1 over, but then instead of writing phi, you replace it with 1 plus 1 over, and you see that this continues forever. So phi, the golden ratio, has this continued fraction. You can go look up in Wikipedia. It will show you that the continued fraction is this form. So the golden ratio has what I think to be the most natural. This would be my first guess at a continued fraction. 1 plus 1 over 1 plus, if I just so happen to somehow think of the idea of a continued fraction. And what I'll do, I mean, the video is mostly over, but what I'll show you really quick is that we can think of this, and if you've taken calculus or anything like that, the farther you take this fraction, the closer to the true phi, 1.618. The farther you take this fraction, the better your approximation of phi is what you're going to get. So what I want to do for the very last bit of the video, I just want to take a little snippet of this continued fraction and show you it's pretty close to phi. So here we go. We're going to do an approximation. So phi, if our continued fraction is correct, it should be, this isn't the best approximation in the world, but 1 plus 1 over 1 plus 1, 1 plus 1 over 1 plus 1 over, and then let's just do 1 plus 1. So we'll stop it there. If you wanted a better approximation, you could do 1 over 1 plus. And what I want to talk about in this and in my videos, so this is just going to be something that you're going to have to deal with, I guess, watching my videos. I personally think that mental math, stuff like that, I think it's important. I think it keeps your brain working. And I know that a lot of people are like, oh my God, fraction, but you can't let numbers bog you down. It's um, just the more you do it, the easier it gets, and I think it's good for you. I honestly like it makes your brain feel good when you crunch some numbers. Okay, so I mean we can do a equal to at this point. This is literally equal to 1 plus 1 over 1 plus, well, so 1 plus 1 is just 2. So see, I bet some people at the beginning were like, oh my gosh, I don't even have any idea how, like, what is this monstrosity up here? You know, this is, just take it one step at a time. 1 plus 1 is 2. So now we have this. 1 plus 1 over 1, 1 plus a half. Well, 1 is the same thing as 2 halves. So 2 halves plus 1 halves is 3 halves. And then you just got to remember, if you have a number divided by a fraction, to divide by a fraction is the same as multiplying by the reciprocal, meaning flip your fraction. So that's how we get this. 1 plus 1 times 2/3. Well, I mean, and so this dot right here, that means times, multiplication dot. Well, that's just 1 plus 2/3. And sometimes I'll use like a calculator approximation. So 1/3 in your calculator is like 0.3333. So 2/3 is 0.66666. So look, we barely took the continued fraction anywhere, and we got a pretty good approximation of phi, 1.66. I mean, it's an overshot, but it's a decent approximation. You know, this should seem like a pretty good approximation for doing such a short amount of the continued fraction. All right, so that's it for this video. I hope you enjoyed it. Just know in the future, I have a stylus on the way, so all of this stuff was just hand drawn. But I hope you enjoyed the video.